Hello, I'm Jake Watkins. You've seen me in such epic, fine quality chemistry educational videos as The Empire of the Empirical Formula and Where Do All the Non-Empirical Formulas Go? Today we're going to look at if you're given the percentage by mass of certain elements, how to find the empirical formula, the compound that they belong to. Okay, and in this case here, we need to talk about what is an empirical formula. Well, an empirical formula is the formula that has the smallest whole number ratios. So, for example of an empirical formula, H2O, we can't break this down any further. We can't have H1O1/2. We cannot do that. We have CO2 where it's 1 carbon and 2 oxygens. We cannot break that down any further. NaCl, we cannot break that down any further. Now, what would be an example of not empirical formulas? Well, for example, H2O2. That is not an empirical formula because these two can actually be divided out. Another example of a not empirical formula is P4O10. Because we can actually reduce this down because we can divide both of them by 2 to get P2O5, which would be an empirical formula. Okay, so that's the difference between the empirical formula and what isn't an empirical formula, which we'll get to in a later video. We'll talk about molecular formulas. Okay, so let's go ahead and let's work out an example. Okay. So we have an unknown substance that's been analyzed, and we found, according to it, it's 72.71% oxygen by mass and 27.29% carbon. So that's what the percentage they gave us. Now, the question they're asking about the empirical formula, well, what is it? That's what they're asking us. Could it be C2O5? Could it be C1O7? That's not happening in this world here. But the idea of, or maybe C1O3, okay? So I'm just giving you ideas. What are the possible combinations that we can have? Well, they gave us the percentages, so that would be a key thing for us to look at. So what is that going to look like? Well, the first thing we want to do is we're going to assume 100 grams of material. We're going to assume 100 grams of material. Now, why in the world are we doing that? Because we want to make this simple. Simple for the rest of us. Okay? We can do calculations easier if we assume 100 grams of the material. So, here's the beauty of it. If we assume 100 grams of material, we can take these and already change them into grams directly. So 72.71 out of 100 grams of material, that means we would have 72.71 grams of oxygen. Now, we don't know how many oxygens there are. We know that the total amount of oxygen in there is 72.71. And we also have 27.29 grams of carbon. Okay, so this is what we have, because if we add those up, it will equal 100 grams, which is kind of cool. That works out very, very well for us. So, now, what is our next thing? Well, great, we've got mass. But how do we relate that to a chemical formula like this? Because remember, we're still trying to figure out what is the formula here. We don't know, okay? So we've got masses. Masses aren't going to do it for us. That means that we're going to have to change it into numbers, okay? We have to change it into numbers, ladies and gentlemen. So, what do you mean, numbers? what the chemist doesn't. And if you don't know what I'm talking about, there's an earlier video where we can talk about grams into moles. You should check that out. That goes into more detail. I will assume that you have that under your belt, so we can go ahead and work with this. Okay, so we're going to change these from grams into moles for both of them. So we're going to convert into moles. And that's what we have. So in this case here, for the oxygen, there's 16 grams per mole. And again, we get that from the periodic chart. Okay. And here, for our carbon, it's 12.01 grams per mole. That's what we have. Okay. So this is what we've got. We're changing these masses, this weight. I've got this amount, this weight of oxygen, but how many oxygen atoms do I have? How many of these carbon atoms do I have actually? That's why we have to change it from mass into numbers. And if you remember numbers, it's moles, basically. That's what we're looking at. And a mole is this giant number. We're not going to worry about that. In chemistry, we treat things as moles. Think of it as the chemist's dozen. If you don't know what I'm talking about, do see a previous video. That will bring you guys up to speed. Okay, so this is what we have. Now we're going to figure out how many moles of each do we have. So 72.71 divided by 16 equals, and I have here 4.54 moles of oxygen. Okay. And over here, I have got 27.29 grams of carbon divided by 12.01 grams of carbon, and I have 2.27 moles of carbon. So that's how many moles I have. Now there's a definite ratio that's there. So what does that look like for us right now? If I wrote up the formula, this is what it would look like. It would be C 2.27 O 4.54. That's what it would look like based on how many moles of carbon and oxygen I have. That's not going to do us any good because remember in chemistry when we work with formulas, we have to work with whole numbers. Okay? So we can't go and round this down. Okay, we cannot round this up either, not now. I'll show you another technique in a moment. But for now, let's finish this problem off. In this case here, what do we need to do? Well, we need to take the smallest number of these two numbers. We take the smallest number and we're going to divide it by itself. Okay, we're going to divide it by itself. Why? Because we're going to reduce it to the smallest number possible. We're going to reduce it that it's going to be 1 carbon. So 2.27 over 2.27 gives us 1 carbon. Here 4.54 divided by 2.27 gets us a 2. So that now we've got this. So our final answer, ladies and gentlemen, is CO2. And that, ladies and gentlemen, is in fact our empirical formula. This is it. This is the answer. Yay! Now, I mentioned something else. What if we had a situation where we had, and I'm going totally off into another unknown realm here, where let's say I've got C1 and I've got O of 2.5. What do? I've reduced this down to the smallest number, but this obviously isn't. This obviously cannot go. This has got to be made into a whole number. The question now comes down to is, what do? I cannot take this and round it up to 3. And I can't take this and round down to 2. I cannot do that. There is that half atom of oxygen there that's kind of annoying. So what we need to do is, how do we make 2.5 into a whole number? Now there's a couple of ways you can do this. If you don't know offhand that 2.5 times 2 is 5, then you could go and multiply it by 10, Okay, and let's say we did it that route. So we got C10O25. Now, is that our empirical formula? Absolutely not, because we can reduce this down to its smallest number. Both numbers can be divided by 5, so if we divided both by 5, C2O5, and that would be an empirical formula right there. Okay? So that's one way to do it. Now, what about a situation where the numbers, it isn't that easy? Let's say, and I have another scenario here where I've got C1O 1.33. Oh gosh, you've got to be kidding me. I can't round up, I can't round down. If I multiply by 10, I'm going to get 13.3. This isn't going to work. How do I make this a whole number? Here's something to think about. 0.33 is 1/3 of something. What if we multiplied it by 3? Okay. Well, if we multiply by 3, we'll have C3O 3.99. You'd say, but wait a minute, that's still not a whole number. Okay, hold on there. This is not as bad as it looks, because this is close enough to round this to a 4. So you've got a C3O4 as your empirical formula. This in real life isn't going to be very stable. It's just not going to be. It's going to react with other things. Okay, looks like my time is done. Hey, I hope you guys enjoy this video. And again, I'm Jake Watkins, signing off.